So, the first speaker today is Daniel Plaumann from the University of Konstanz. We speak about hyperbolic polynomials, interlacers, and sums of squares.
Thank you, Marcus. Thank you very much. Good morning, everyone. I'm very happy to be here. Thank you for the opportunity to be able to speak here. So, I will speak about joint work with Mario Kummer from Konstanz and Cynthia Vincent from Michigan. And so we will be looking at two kinds of real polynomials. So let's say I have a homogeneous polynomial f of degree d, and I'm interested in two kinds. One is certainly extremely familiar, positive polynomials. F is everywhere non-negative on Rn. And of course, we know the happiest that such a polynomial can be is if it's a sum of squares. That's the ideal representation of a non-negative polynomial. And the second kind of polynomials is the hyperbolic polynomials. So if you've been to Tim's talk, you're certainly familiar with those. So the ideal representation of a hyperbolic polynomial is the determinant of a linear symmetric matrix pencil, which is somewhere positive definite. So you have symmetric matrices M1 to Mn, and some point where the linear pencil spanned by M1 to Mn is definite, and then you take the determinant. And the general definition of a hyperbolic polynomial I put down here again. So you have this point E, which is fixed, and just the general polynomial is hyperbolic with respect to that point E if it's positive there. And if you look at lines in direction E for all v and Rn, f of v minus Te has only real roots. So, I mean, in some sense, these are on opposite ends of the spectrum. So, say if f is strictly positive, this means it has no zeros. Whereas here, for hyperbolic polynomials, in particular in one variable or homogeneous in two variables, this is a polynomial with only real zeros. It's the exact opposite. And you have in both cases these characteristic representations, sums of squares and determinantal representations. And in both cases, it's known that these representations cannot always exist. It's only in exceptional small cases. So for the sums of squares, only if n is at most 2 or d is at most 2, or the one non-trivial exceptional case, n equals 3 and d equals 4 due to Hilbert. And likewise for determinantal polynomials, such representations, for hyperbolic polynomials, such determinantal representations are guaranteed to exist only if n is at most 3. That's the Helton-Winikoff theorem, which the non-trivial part of the statement, the existence, is the Helton-Winikoff theorem. So let me briefly look a bit more at these hyperbolic polynomials that you should have seen already on Monday. So that's the definition again. So all roots of f of v minus Te are real, and of course I'm writing it down like this to make it look like already look like a characteristic polynomial, right? This looks like the characteristic polynomial of a matrix, and you should think of these hyperbolic polynomials as sort of generalized characteristic polynomials. And in particular, any hyperbolic polynomial defines a cone, which is not completely obvious, but it's true. If you have a hyperbolic polynomial, you look at the set of all directions where all these roots are non-negative, and this defines a closed convex cone, which is called the hyperbolicity cone of this polynomial f. I have a picture up here. So you see the convex cone in the inside, and then you have all these other real roots of the polynomial that are sort of wrapped around this cone. So this is for d equals 4. If you had d equals 6, you would have another layer around the cone in the middle. And of course, if you actually have a determinantal polynomial, then the hyperbolicity cone is just a spectrohedral cone defined by these matrices because, well, say if m of e, this one fixed point, is the identity, then f of v minus t is simply the characteristic polynomial of the matrix m of v. And so these two coincide, and this gives you the spectrohedral cone. You can think of this in terms of optimization. So for non-negative polynomials, you want to know whether a polynomial is non-negative. You relax this to the question of whether it is a sum of squares, which you can encode into an SDP. And there's a somewhat, if you want, somewhat similar problem for hyperbolic polynomials. If you have a hyperbolic polynomial, you have what is called a hyperbolic program, the task of optimizing over the hyperbolicity cone. And so these hyperbolic programs were studied in the beginning in the 90s, I think by Güler, Lewis, Rennegar, Tunfel, and others. And they behave very much like semi-definite programs. So the hyperbolic polynomial, you take minus log of f. This provides a barrier function, and you can work very much as with semi-definite programs. But on the other hand, you may also want to look at semi-definite relaxations of these hyperbolic programs. This is related to finding determinantal representations of hyperbolic polynomials. And so why do I insist on this somewhat vague analogy between non-negative polynomials and hyperbolic polynomials? It's well, because I want to demonstrate that there is actually a deeper connection between these two problems. And well, to begin with, you can actually rewrite the hyperbolicity condition into a non-negativity condition. And to do this, I need the notion of an interlacer. That's also something that's quite classical in the study of hyperbolic polynomials. So suppose you have a hyperbolic polynomial f, degree d, and we'll always assume that it's irreducible for simplicity. And suppose you have another hyperbolic polynomial of degree 1 less. Then we say that g is an interlacer of f. Well, if the zeros of g are sort of nested between those of f. So, I mean, the correct definition would be, so here you restrict to some line, you have the roots of f and the roots of g, and then the roots of g are always between the roots of f. And in the picture, this would look like this. So the 3D picture starts to look a little confusing, so it's actually nicer to look at linear slices or projective pictures if you want. So here's a quartic together with a cubic interlacer. And the point E is here in the interior, which means that sort of on this line it's at infinity. So that's why it looks like this. There are no zeros inside here, and you have the nesting outside of the hyperbolicity cone. So that's what topologically what the picture should look like. And if you have a hyperbolic polynomial, so there are sort of two natural sources of interlacers. One is you can take directional derivatives. If you take a directional derivative with respect to any direction in the hyperbolicity cone, you get an interlacer. And that's just, well, okay, so for v equal to e, this is basically just Rolle's theorem. If you have a polynomial with only real zeros, you take the derivative, then the zeros of the derivative lie in between. And then it's not so hard to show that it doesn't matter if you shift around in the hyperbolicity cone. So for any direction in the hyperbolicity cone, you get an interlacer if you take the derivative in this direction. And the other, not completely unrelated source of examples is if you actually have a determinantal polynomial, then any symmetric maximal minor of this matrix, and that will be polynomials of degree d minus 1, those are also interlacers. It's not quite as clear, but it's true. And so if we look further at these interlacers, the next thing that's not hard to see is if you have two interlacers, here I have a picture, a quartic curve with two different cubic interlacers, then, well, the product of two interlacers is non-negative on the zero set of f, because each interlacer alternates signs, and I fix the sign at the point E. So if I take the product, I get something that has the same sign in all the roots of f. So the product of two interlacers, no matter how they may, of course, intersect in a complicated way, but on the zero set of f, they will be non-negative. So this gives you a non-negativity condition. And what you can show, in fact, is the following. So you can show that the set of interlacers for fixed f, the set of all interlacing polynomials, is, in fact, a convex cone. And has an explicit description. You look at this expression here. The derivative of f in direction e multiplied by g minus f times the derivative of g. And if this is non-negative, this is if and only if g is an interlacer. So this condition characterizes the interlacers. And the reason is basically just if you reduce to one variable, it's a very classical thing about polynomials in one variable. If you have two polynomials with only real roots, and one of them has degree 1 less than the other, then you have this interlacing property if and only if this so-called Wronskian, which is the numerator of the derivative of the quotient, so fg prime minus f prime g, is positive or negative. So this gives you, well, in particular, it shows that the interlacers form a convex cone. And now, on the other hand, so let me keep this up here, you have this description of the interlacer cone. And then, on the other hand, I told you if you take a directional derivative in a hyperbolic direction, you get an interlacer. And again, this is if and only if. So if you take a directional derivative of f, it will be an interlacer if and only if the direction was in the hyperbolicity cone. It's not too hard to show. Once you run out of this cone, you will have some non-interlacing going on. And so if you put this together, you get a description of the hyperbolicity cone, which at first looks a little confusing, but it's in principle clear from what we have said. So the hyperbolicity cone is the set of all points for which this is a non-negative polynomial, right? Because dvf is an interlacer if and only if v is in the hyperbolicity cone, and it's an interlacer if and only if this polynomial is non-negative. So I get this family of Wronskians, which are all the polynomials of this form. And, well, you say you fix E and you vary V. That's a linear family in V. So it realizes, this description realizes the hyperbolicity cone as a slice of the cone of non-negative polynomials. So any hyperbolicity cone is a slice of the cone of non-negative polynomials. Well, it depends. There can be more. There can be more. So I'll say something towards the end. If I still have time, I'll try to say something about sort of the cone of all interlacers. It's not so easy to understand, but we do know a few things. So this gives you this description of the hyperbolicity cone in terms of non-negative polynomials. So now, of course, once you have such a description, you can play the usual game. You can look at sums of squares relaxations if you want. So this gives you, an inner approximation of the hyperbolicity cone. You just require this Wronskian to be a sum of squares, or maybe if it's not a sum of squares, you can also look at a hierarchy where you allow denominators and multiply with such a polynomial sum of xi squared raised to the power of n. As n grows, this will hopefully give you a better and better approximation of the hyperbolicity cone. That's a standard thing. It's a result of Resnick. That any non-negative polynomial, well, any strictly positive polynomial will be a sum of squares if multiplied by some sufficiently high power of such a polynomial. And so in particular, what you can get from this, if your polynomial is strictly hyperbolic, meaning the hyperbolicity cone is smooth, then this will be a better and better approximation of the hyperbolicity cone. So let me briefly mention this is related to other recent results on representations of hyperbolicity cones by spectrohedral cones. So on the one hand, there's a result of Netzer and Sanyal, which also says if f is strictly hyperbolic, then in fact it is a projected spectrohedral cone, so a spectrohedral shadow. And so this follows sort of from general representation results under smoothness assumptions. So it's, on the one hand, it's much less explicit than this family of Wronskians. On the other hand, in the smooth case, you have guaranteed finite convergence at some point. And also there is a result by Pablo Parillo and Jim Saunderson for derivative cones of spectrohedral cones, which I think Tim also spoke about at least briefly. So on the one hand, this description of the interlacer cone by this non-negativity condition gives you some way of relaxing hyperbolicity cones to spectrohedral cones. But on the other hand, this hyperbolicity, this interlacer cone, together with this description by the Wronskians, it contains much more information. It contains a lot of the information that you want when trying to decide whether the hyperbolicity cone is spectrohedral or whether your polynomial has a determinantal representation. So let me go into some of these results. This is now a bit more on the algebraic geometry side. So on the one hand, I just want to mention this along the way. This is from a result from an earlier paper with Cynthia Van Zandt. In the case of curves, you can use the theory of these interlacers to understand the Helton-Vinikoff theorem. So if you have a hyperbolic polynomial in 3 variables, Helton-Vinikoff will tell you that it has a determinantal representation, a symmetric determinantal representation. And in fact, if you allow, instead of symmetric, if you allow Hermitian determinantal representations, so it's a weaker result than Helton-Vinikoff, but then you can actually produce such a representation starting from any interlacer in an explicit and basically elementary way. So yes, homogeneous. I'm sorry, the polynomials are always homogeneous. In fact, here I have a picture of a quartic together with a cubic interlacer. So in fact, what will happen is that this interlacer that you fix will show up as a symmetric minor of the determinantal representation that you construct. It's sort of reconstructing the representation from the minors. And on the other hand, the full cone of interlacers and these Wronskians, that's also related to determinantal representations. So to begin with, we can show the following. If your polynomial has a determinantal representation, or even weaker, if some power of the polynomial has a determinantal representation, then in fact all these Wronskians we were looking at are sums of squares. So this is really a strong connection between determinantal representations and sums of squares representations. Any determinantal representation will yield a representation of the Wronskians of this family as sums of squares. So of course, if you think of it in terms of this hyperbolicity cone approximating it, this is of course not so useful at first, because if you already have a determinantal representation, then what this will give you, you have a nice representation already as a spectrohedral cone, and this will give you some terrible representation as a projected spectrohedral cone. On the other hand, you might, for instance, know from abstract reasons that your polynomial must have a determinantal representation, but you might not know what the representation is. And this, in fact, might be easier to compute than the determinantal representation. But more importantly, to my mind at least, it shows somehow that this approximation with these non-negative Wronskians is somewhat sensible. I mean, it definitely becomes exact if you already know that the hyperbolicity cone is spectrohedral. And we can also use this and apply it to an example by Peter Brandijn, which I think Tim also mentioned. So there's this polynomial called the Vamos polynomial. So it's not terribly important what exactly it is, but it is a degree 4 polynomial in 8 variables, constructed from this matroid. And this polynomial is hyperbolic. That was shown earlier by Wagner and Wey. It's not so easy to show. In fact, also uses some of this Wronskian business. And Brandijn showed no power of this polynomial has a determinantal representation. And indeed, we can try to use this theorem, we can in fact show that there is a Wronskian for this polynomial, namely direction E7 and direction E8, which we can show is not a sum of squares, which again implies Brandain's result, showing that this polynomial cannot have, no power of this polynomial can have a determinantal representation.
Wronskians are all proportional for all the powers, right?
Well, not quite proportional, but there is an easy, I mean, it's easy to say what happens to the Wronskian if you take a power. They're not proportional exactly, but no, I can show you later. Almost. They're strongly related. So I mean, there's absolutely no reason to believe in the converse of this theorem. So if you knew that all the Wronskians are sums of squares, would this imply that some power has a determinantal representation? That seems highly unlikely, but it's also somewhat difficult to to find a counterexample, because basically, until now, this Vamos polynomial is the only explicit example that we know of a polynomial where no power, a hyperbolic polynomial, such that no power has a determinantal representation. And for this, we know that there's some Wronskian that's not a sum of squares. It's not so easy to find some other example. So there is this strong connection between determinantal representations and sums of squares, but it's unlikely that it goes either way, at least not in a straightforward way. This Vamos polynomial, like other polynomials that come up in matroid theory, it's not only homogeneous, it's multi-affine. It has degree 1 in each variable. And in fact, in this case, we can say something more. In fact, there is a converse. So if you have a multi-affine hyperbolic polynomial, then we can indeed show that it admits a determinantal representation. So not with powers, just the polynomial itself admits a determinantal representation if and only if the Wronskians are not only sums of squares, but squares, actual squares. So for instance, this was classically known, but it's also easy to say in this way. If you look at just elementary symmetric polynomials, those are multi-affine polynomials, and they are, in fact, hyperbolic with respect to the point 1, 1, 1. Then this was, well, I say it's a classical result, in fact, so classical that I'm not quite able to attribute it to any particular paper. I can only show you papers that claim it's classical. But
what's the oldest one of these?
2 years. So, no, maybe a few more. I'm not quite sure. But anyway, so this seems to be in the literature. So the elementary symmetric polynomials admit determinantal representations only in exceptional cases, namely the first, the nth, and the n minus first. There's a duality, in fact, between the first and the n minus first, also with respect to determinantal representations. So these are the exceptional cases, and in all other cases, you do not have such a representation, and this you can easily show by computing these Wronskians and check whether they are squares. Okay, so to close, let me tie in a little bit with maybe with Bernd's talk. So what is this full cone of interlacers? It is some cone attached to our hyperbolic polynomial, and it contains a lot of the information that we want. So what can be said about this full cone? First of all, okay, this I did not put on the slides, but first of all, it's not so hard to give examples. In general, it's not itself a hyperbolicity cone. It's not the hyperbolicity cone of some other polynomial, which you might maybe think. This is definitely not true, but it is some semi-algebraic cone. So for instance, if you take the full determinantal polynomial, then it's not too hard to show that what you get back is indeed also the PSD cone. This is a deceptively simple case. But in general, it contains the hyperbolicity cone, but it can be much bigger than the hyperbolicity cone. So come back to Emmanuel's question, there are interlacers that are not directional derivatives. And so what we can try to do is we can try to compute its algebraic boundary. And this is fairly simple in the smooth case. Again, with the usual assumptions, if we look at algebraic boundaries, we forget the real numbers, and we have to make a smoothness assumption. We pass to C. If you look at the algebraic boundary of the cone of interlacers in the space of complex polynomials of degree d minus 1, then it's this description. And this description just says it's pretty much what you think it would be. It's the set of polynomials that are somewhere tangential to the thing that you're looking at. If you have an interlacer and it becomes sort of extremal, then at some point it has to touch the hyperbolicity cone, and that's exactly this condition. And this is then not so hard to show from general principles. In the smooth case, that actually defines an irreducible hypersurface, which must then be the algebraic boundary. But this is in the non-smooth case, which for this theory would be very interesting. This sort of breaks down. I mean, you can no longer show the irreducibility. It's probably not true. So for a singular case, it would be interesting to understand the algebraic boundary of this interlacer cone. So okay, let me close with some references. So everything I talked about is in this preprint. There is a follow-up that I want to point out to you, because I didn't mention it in the talk, by Mario, who's now a grad student in Konstanz. So we use some of his ideas to show that this Vamos polynomial, or at least a certain variant of this, a certain specialization of this Vamos polynomial. So we know it admits no determinantal representation, but he still constructed a spectrohedral representation of the explicit spectrohedral representation of the hyperbolicity cone. Okay, thank you very much for your attention.
So any questions? No questions. So when I have a question, the last slide, can you go back?
Yes.
So I just, yes, this one. So I just didn't understand it. So you take the joint matrix of X.
Yes.
So this is a matrix of polynomials.
Right.
And then you get polynomials, right?
Sure, I want polynomials. I mean, this should be the interlacer cone, right? I want polynomials
with
d minus 1.
for the interlacer.
Yes.
Okay. Okay.
Let me ask a question. So the determinant, of course, is not smooth,
right,
in this sense.
Yes.
But let's pretend it were, and you carried out this construction. Have you computed this for the determinant?
No. No, I haven't tried. I don't know what would happen. I would guess that it would give a very wrong result, but I haven't tried.
So this condition that these Wronskians are, not one of them is not a sum of squares. This is an open condition, right?
Yes.
So you do have a proof that there are more polynomials beside the Vamos.
Yeah, I know. That's right. In a way, yes. But we somehow have. That's true. But this is somehow. I mean, it's an open condition, but you never quite know in what direction to go, how far, right? So you can theoretically you can do some perturbation, but you have no nice explicit examples like the Vamos polynomial. But yes, that's true. So in some sense, you have a neighborhood with this problem.
No other questions? Then let's thank Victor again.